Hey everyone, welcome to APCTP Colloquium series. My name is Jung Gi-yoon. I'm a junior research group leader in APCTP. Today, I'm the chair of the APCTP Colloquium. It's my great honor to introduce today's speaker, Professor Leonard Susskind. He is a Felix Bloch Professor of Theoretical Physics at Stanford University. And he is the founding director of the Stanford Institute for Theoretical Physics. Furthermore, he is a member of National Academy of Science and American Academy of Arts and Sciences. He is an associate member of Pertinent Institute for the Theoretical Physics in Canada. And he was also a distinguished professor at KIAS in Korea until 2016. He won Sakurai Prize for Theoretical Physics at 1998. And also he was awarded Oscar Klein Medal in 2018. He is a great pioneer in string theory and the black hole. He always provides creative, inspiring ideas to physics community. And his idea always sparked revolutions in physics. His contributions to physics are enormous, so that it will take another hour to introduce his contribution with details. So let me briefly mention his original proposals. He proposed BFSS model and the giant graviton, staggered fermion in the lattice field theory, string theory landscape, and holography was first proposed by Tufte, but Susskind provided a precise string interpretation on holography. And he also proposed holography in the flat space limit, ER equal EPR proposal, black hole complementarity, complexity and the action conjecture, etc. I cannot list all of them. Today, he will tell us another new story about the aspect of digital holography. Let's see how he will bring another revolution this time. Please join me in welcoming our speaker, Professor Susskind.
Okay, are you ready? All right, you are more optimistic than some of my friends, and even more optimistic than I am about whether this will prove to be a revolution in physics. I do think that there is a close connection between de Sitter space and a particular theory that I'll describe. It's called double-scaled SYK theory, but I'm much less certain about it than I was about many of the other things you described when I first put them forward. So what I'm going to do today is describe why I think that the incidentally, I'm going to assume that my audience is an audience largely of theoretical physicists. Is that correct?
Yes.
Okay. And that people have kept up to some extent with the developments in this subject. The SYK theory is a very well-known theory to a group of people who I know very well. I don't know if it's as well-known outside of my particular area. But I'm going to show you basically why I think there are connections between the two of them and how those connections work. Let's begin with de Sitter space and take an astronomer's viewpoint to de Sitter space. We sit at the center of a thing called the static patch. Of course, we don't yet live in de Sitter space, but in time, we may live in something very, very close to de Sitter space. We in our galaxy will be sitting at the center of what we call the static patch. And when we look around us, we'll see very little, except for some fluctuations now and then. The fluctuations might be interesting, but we'll largely see empty de Sitter space. And out at the boundary of that empty de Sitter space, there will be a horizon. The horizon is where the holographic degrees of freedom have to reside. They have to reside at the boundary of the observable universe. And the holographic principle would say here that the entire interior of the static patch, our world, so to speak, our observable world, would be described by a theory living on the horizon with a number of degrees of freedom that would be familiar to you, the area of the horizon divided by 4 times the Newton constant. But then that raises the question, what are the holographic degrees of freedom? What is their dynamics? And what is the dictionary that connect them to the observable phenomena? We need concrete examples. We absolutely need concrete examples. My concrete example may or may not be the right one. Well, it's certainly not the right one for our world, but it may not even be consistent. But we do need concrete examples, and it seems to me this is something that we should be very, very involved with. All right, what I'm going to talk about is something called SYK Infinity. DS does not stand for de Sitter space, it stands for double-scaled. Double-scaled SYK system evaluated at a formal temperature which is infinite. And the conjecture, which I put forward actually a couple of years ago now, I think, is that SYK Infinity is dual to a particular kind of de Sitter space, a particular version of de Sitter space. A similar proposal was put forward by Herman Verlinde, never published, but he was on record as having put this proposal forward. The question mark here indicates my lack, or at least my and my fellow physicists, some of whom are at Stanford, indicate a lack of certainty that this is right, a certain tension, and I cannot guarantee that it's right. Of course, I can never guarantee that anything is right, but I can guarantee less that this is correct than for most things that I've been involved with. Nevertheless, I'll explain to you what the issues are, and I suspect the same issues are going to come up in any version of holographic de Sitter space. Okay, that's number one, DSSYK. Number two, I'm going to tell you that the DSSYK system has features which are very similar to large N QCD. And in particular, they have the feature of having confinement. And when I say confinement, I mean confinement very similar to quark confinement. And what the role of that confinement is in being consistent with what we know about de Sitter space. Let me say it this way, the slogan is that almost everything is confined in de Sitter space. That will have to be true whether or not we're talking about this DSSYK system or some other holographic system. And so I think there are certain things here that I am fairly confident about. Good. What is the framework? The framework is what I'll call static patch holography. The study of the static patch of de Sitter space, or a static patch of de Sitter space, holographically, by degrees of freedom which are localized on the stretched horizon. So here's a Penrose diagram describing two static patches of de Sitter space. It's all of de Sitter space, but in fact, two static patches, one which I call the antipode, the other which I call a pode. It doesn't matter what I call them. They're two opposing complementary static patches. And the green region is the stretched horizon, a region very near the horizon, but slightly away from it. The holographic degrees of freedom are supposed to be on that green surface. And our job is to try to reconstruct what's going on inside the static patch, the objects which can inhabit that static patch, and their behavior, and show that it's consistent with de Sitter space, with a de Sitter space interpretation of the static patch. That is what we would like to do. How close are we, or how close am I to doing that? You would be the judge of that. Now there is a puzzle. The puzzle goes something like this. DSSYK Infinity, or for that matter, any holographic theory of de Sitter space, has a very large number of fundamental degrees of freedom on the horizon. It has to have enough degrees of freedom to describe the entire entropy. But in the case of the DSSYK system, it has n species of massless, nominally massless fermions that I will call chi-I. Chi-I are fermionic degrees of freedom. If all of these represent quanta that can escape into the static patch, and escape into the static patch means escape as Gibbons Hawking radiation. Radiation emitted by the horizon into the static patch, there would be far too many quanta in the static patch. Roughly, there would be far too many of them. Here's a picture of a Hawking quantum being emitted into the static patch. And roughly speaking, we should expect that there is about one Hawking particle in the static patch at any given time. That's a surprisingly small number, but that's what follows from standard thermodynamics. If every one of these fermions could be emitted into the static patch, there would be an enormous number of them. And that's not consistent with a local theory of the static patch. So the question is, what is the holographic mechanism that keeps these degrees of freedom from escaping the horizon? And the answer that I will propose is a kind of confinement. Now, when I say confinement can mean a lot of different things, but when I say confinement here, I mean something very similar to quark confinement in gauge theories, in QCD. Let's begin then with the gravitational side of the duality. On the gravitational side, let's begin with de Sitter space. Now over here, ds does mean de Sitter space. 2 + 1 dimensional de Sitter space, and dimensionally reducing it, I'll show you exactly how in a moment, until it becomes a 1 + 1 dimensional theory, namely JT, Jakob-Teitelbaum gravity, except slightly unusual, a de Sitter space version of it, which means the cosmological constant in the geometry is positive. I'm not going to go through that in detail, but if we were to take 2 + 1 dimensional de Sitter space, this is it. Standard, this is the metric of the static patch. Alpha here is an angle. It goes from 0 to 2 pi. We're going to dimensionally reduce things by assuming nothing depends on alpha and just getting rid of the alpha coordinate. That gives us a metric, which is just the metric of 1 + 1 dimensional de Sitter space, but also gives us a field. The field represents at any point, at any radial distance, the radius of the local two-sphere. No, it's not a two-sphere, it's a one-sphere, the local circle. So there's a scalar field, the dilaton, which is proportional to r. That is a solution of the JT gravity system with positive cosmological constant, and that's all I'm going to say about it, at least for now. Well, it's not all I'm going to say about it, but it's all I'm going to say about the details of the general relativity. Now, a very, very important set of concepts has to do with the mass and length scales in de Sitter space in the semi-classical limit. By the semi-classical limit, I mean a limit in which the entropy, in which the horizon size, oh, let me come back here for a moment. This parameter LC, that's interpreted as the cosmic length scale in the problem, the Hubble scale, if you like. In our world, it would be some tens of billions of light years. Okay, the semi-classical limit is the limit in which the horizon radius, the de Sitter length scale, and the entropy is so large that it might as well be considered effectively infinite for many purposes. Semi-classical limit means just a very, very big de Sitter space. And we are interested in the various length scales which appear in its description. I'm going to start with 4 dimensions because it's familiar. What is the largest mass you can put into a de Sitter space? The largest mass you can put into a de Sitter space without completely ruining the de Sitter space somehow is roughly of order of magnitude the mass of a black hole which would fill up the static patch. Here it is, or almost fill up the static patch. That corresponds to a mass, and again, we're in 4 dimensions, which the Schwarzschild radius is replaced by LC, divided by the 4-dimensional Newton constant. This is the standard relation between mass and horizon size. And that would tell us the largest mass we can ever expect to put into this de Sitter space is of order LC over G4. What is the minimum energy? Is there a sense in which there is a minimum energy? And the answer is yes. The minimum energy corresponds to a wavelength which is so long that it can just barely be contained in the de Sitter space. If the energy of some particle, for example, is sufficiently low, the corresponding wavelength will be very large, be h, and our condition in order to be able to put it into the de Sitter space is that that wavelength be smaller than the radius of the de Sitter space. That gives us a minimum mass, which is h bar over LC, which is also the Gibbons Hawking temperature in de Sitter space, the Hawking temperature in the de Sitter space. Now I want to introduce another scale. The other scale is neither so big that it's anywhere near M max, not so small that it's anywhere near M min, but somewhere in between. And these correspond to mass scales, which are so in between, they're sandwiched between these extreme scales, that the study of physics at those scales doesn't really care very much about whether it's in de Sitter space or flat space. The little m here stands for either micro, it could stand for micro, it could stand for middle, or it could stand for mean. Geometric mean of the biggest scale, biggest mass scale, and the smallest mass scale. And if you work it out, you just multiply these two and take their square root, you get h bar over g4 to the 1/2 power, and that is nothing but the Planck scale in 4 dimensions. So this median scale is the Planck scale. There is one more important scale in what we'll talk about, which is the string scale. The string scale is typically G. What is G? G is some string coupling constant times the Planck scale. And so here's the picture we get of the set of scales, which is going to be important to us. At the highest scale is M max. At the lowest scale is M min, which is also equal to the Hawking temperature. And in between, we have this middle scale, middle, micro, median, whatever you want to call it, which happens to also be the Planck scale. This is 4 dimensions. And somewhat below it, assuming that G is less than 1 here, is the string scale. This should be familiar to you, even though we've probably never drawn this diagram before, but the concept should be familiar. Associated with these length scales, in particular M min, MS, and M middle, there are length scales. The length scales are simply given by h bar divided by the mass scales. LC is the length scale associated with the cosmic scale is what is it? It's basically the wavelength of a Hawking quantum. LM here, well, since M here is the Planck mass, that'll just be the Planck length. And LS, what is that? That's just the string length scale, whatever the string length scale happens to be. Okay, that's 4 dimensions. Now, surprisingly, in 3 dimensions, the situation is a little bit different, both very similar and very different. First of all, the maximum mass that you can put into de Sitter space is the Planck mass itself. That seems a little bit odd, but it's true. In 3 dimensions, the presence of a mass creates a conical deficit, a little bite taken out of the geometry, an angle taken out of the geometry. As you let the mass go to the Planck mass, the angle deficit goes to 2 pi. So the biggest mass you can put into 3-dimensional de Sitter space is, in fact, the Planck mass, which is 1 over G3, G3 being the Newton constant in 3 dimensions. The minimum mass is exactly as it was before, the energy corresponding to the longest wavelength, which can just barely fit in de Sitter space in the static patch. And now we can calculate this median mass again, the one which is sort of halfway in between, and roughly speaking corresponds to the energy scales, which don't really depend very much on the radius of the de Sitter space. It's in between these two limits that we get just by multiplying and taking the square root. And it's some expression here, but in particular, it's not the Planck scale. It's just MM, the mean scale. Now, what about the string scale? Is there a string scale? I will maintain there is something very much like a string scale in the SYK system, but instead of characterizing it just by its mass, I'm going to characterize it by a parameter lambda by saying the string scale, the ratio of the string scale to this microscopic scale squared is equal to lambda. That's a definition of lambda, if you like. And we're going to assume that in the semi-classical limit, lambda is finite. That's equivalent to saying the string scale is comparable to this microscopic scale m sub n. So we get a picture which looks very much like the four-dimensional picture, except up at this end is the Planck mass. Down at this end is still the Hawking temperature. In the middle is this median scale or middle scale, microscale, which is not the Planck scale this time, but I will assume that the string scale is not too far away from this, and at the limit in which the semi-classical limit, the ratio of m string to m micro stays constant, stays fixed. Those will be my assumptions. Now, that's on the bulk side. Yes, question.
Yeah, I think I didn't understand this part. So what's the difference between 4D and 3D? Why the black hole mass?
In 4 dimensions, up here was the maximum size black hole that you can put into de Sitter space. It corresponds to the Nari black hole, roughly. And it's a huge, huge mass, many, many, many times bigger than any microscopic mass you'll ever consider. In 3 dimensions, what's up here is the Planck mass itself. The Planck mass in 3 dimensions is enough to completely and radically destroy the de Sitter space. You cannot put in a bigger mass than that. Remember, the reason is because a mass creates a conical deficit, and a conical deficit, if it's up near 2 pi, will essentially destroy the entire geometry. So there is a big difference in that respect. On the other hand, this line is very similar. It goes from some maximum to some minimum with an intermediate micro scale in between and a string scale somewhere nearby. So the two diagrams are both very similar and very different. Similar in going from one extreme to another with things in between. But what occurs up at this end in 3 dimensions is the Planck scale. Now, if you're not familiar with that and you're interested in 3-dimensional de Sitter space, my advice to you is get familiar with it because it may be one of the most important facts about 3-dimensional de Sitter space, just as you should be very, very familiar with this picture in 4 dimensions. Okay, now let's keep going. Let's now move on to the other side of the duality. The other side of the duality is the DSS of SYK sub-infinity system. So let me define it quickly for you. I'm going to assume you have a working knowledge, or at least a semi-working knowledge, of the SYK system. It's composed of a set of fermionic modes. N of them, where n is large, of order the entropy of the de Sitter space. They satisfy conventional anti-commutation relations. I put a 2 there because if I put the 2 there, I'll get rid of a whole bunch of 2s that would occur otherwise. These J's are picked from Gaussian random ensemble. They're random variables, but once they're picked, they're picked. They don't depend on time, and they have a variance, which is q factorial over n to the q minus 1. This is slightly different than the standard normalization. It corresponds to a different choice of energy units. Instead of using the standard energy units, I am using units in Hubble masses, in Hubble units for the de Sitter space. It's not very important. It's just an important thing to remember that some of my expressions would change a little bit with standard normalization, but all it corresponds to is a change of units, a change of units for time and energy. So I won't spend much time on it. This is more or less standard, except for a factor of Q, which has to do with a change of units from string units, basically, to cosmic units. Now, of course, the other thing we always do in an SYK system is let n go to infinity. That's the semi-classical limit in which the entropy becomes effectively infinite. That would be the standard SYK system. The double-scaled system is defined, or sorry, the usual system would be Q, this Q here, fixed. Q fixed, the standard Q parameter fixed. In double-scaled SYK, we allow Q squared over N to be fixed, equal to a parameter that I'll call lambda. Now, wait a minute, I've already previously introduced a lambda. Where is it? Here it is, right over here. M string over M micro squared, I called lambda, and I assumed it was finite in the limit. Here I've introduced another lambda. No, it's the same lambda, but we will show that that's the same lambda, that these two lambdas are the same. So bear with me. At the moment, it's not obvious they're the same. One is related to the ratio of mass scales, and the other is related to the ratio of Q squared and N. Now, finally, the last funny thing in DSSYK sub infinity is that the formal mathematical temperature that goes into the Boltzmann distribution is infinite. That does not mean that the Gibbons Hawking temperature is infinite. The Gibbons Hawking temperature is an emergent quantity which will emerge out of these assumptions. The assumption that the temperature is infinite is closely related to work, to observations made by, who was it, Chandrasekharan, Longo, Pennington, and Witten in a recent paper, and also the paper by Lin and myself. And I won't go into it very much here. We won't use it. We will use it. We'll use it extensively, but I won't mention it much again. Yeah.
I want to ask one question.
Again?
I want to ask one question about the limit. You said that you need to take the finite limit for the Q squared over N.
Yes.
But I think you need to require that the Q is an integer.
Oh, Q is an integer and N is an integer also, yes.
Okay. So, but if you take any finite N, you take any finite lambda, then Q should not be integer. Is this
well,
right?
Okay. Yes, of course you're right, but Q squared being the closest Q that you can get to the square root of N. How about that? Or lambda times N. Yeah. I don't think there's any problem with taking this limit Q squared over N. If there is, yeah.
Maybe I said my question, my worry about it. Because a different Q will give you a different Hamiltonian. So I worry about it. You do not have the continuum limit for the Q.
Yes, I understand what you're saying. You say the theory might behave erratically.
Yeah.
And jump around a little bit. It is possible. It is possible. I never gave that much thought. I always read the papers and said, okay, Q squared over N is kept fixed. And you're right. It is something we should worry about. I don't disagree with you.
Okay.
All right. Having said that, I'm not going to worry about it.
Okay.
Right. Okay. Now, let me give you a dictionary between the two sides of the duality. First of all, and I'm not going to justify it now. I'm just going to tell you this is the dictionary which seems to emerge from thinking of the DSSYK system as de Sitter space. First of all, the minimum mass scale, the Hawking temperature, corresponds to this parameter J, the parameter J that occurs in the variance here. It's a fundamental parameter of the DSSYK system, and it appears to be the minimum energy that one can put into the DSSYK system. The maximum mass is just J times N, where N is this big number. And the median or mean mass halfway in between them logarithmically is, of course, j times the square root of n. Now, let's go to the string mass scale. I haven't even told you why I think there are strings in the theory, let alone why there should be a string mass scale. But let me just note that if the string scale happens to turn out to be q times j, q is a big number, it's the square root of a big number, then the ratio of these two, of the string scale to m, will exactly be q squared over n. The j's will cancel, and we'll get q squared, or just as I originally defined lambda. But the point is that if this can be shown to be true, then we will have shown that the two definitions of lambda, one in terms of gravity quantities, string scale, the median energy scale, and the other in terms of SYK systems quantities, are the same. So we have to keep that in mind. It would be interesting to have a reason to believe that the string scale or some non-perturbative scale was q squared over n. We'll come back to that. We'll return to that. But before I do, I want to go through a little bit about perturbation theory, ordinary perturbation theory in the SYK system. Perturbation theory is quite easy here. The fermions are the fundamental constituents. The vertices correspond to the terms in the Hamiltonian where q fermions interact. Those are the terms in the Hamiltonian, chi1, chi2, chi3 up to chi q. So q fermions, here q is 6. All right, so a vertex corresponds to q fermions. At each vertex, there are some red dotted lines which also come in. These red dotted lines are associated with averaging over the ensemble of j's. Come back to in a minute. The propagators of the fermions are very simple in the infinite temperature limit. They're just epsilon, where epsilon is the sign function, not SINE, but SIGN, the sign function of T2 minus T1. In other words, it's 1 if T2 is greater than T1, minus 1 if T2 is less than T1. And the propagators for these dotted red lines are simply the variance of the J coupling constants, J squared Q factorial over n to the Q minus 1 that I described earlier. All right, so let me show you how you calculate a simple diagram. Here's a diagram. You could think of it as a kind of vacuum diagram, vertex, vertex, and propagators in between. First of all, you have to, the first factor here represents the number of ways of choosing Q fermions out of a total of n. Which Q fermions go in here out of a total of n possibilities, and that's n to the Q over Q factorial. It's n choose Q, but I've made a Stirling approximation to n choose Q. So that tells you how many different ways there are of assigning the labels on these lines here. Next, there is this red correlation function here between here and here. That's J squared over Q factorial over n to the Q minus 1. And finally, there may be some reason why we would like to integrate this over time. Things are only functions of time. There is no space now. We might have reason to want to integrate this over the relative time between the two vertices. And since the propagators here are all either 1 or minus 1, and there's an even number of them in here, the product of propagators is just 1, and we just get an integral dt. That's a little odd, just a pure integral dt with nothing to regulate it. But let's take it for what it is. Our answer then, working all of this out, is just J squared integral dt times n. Now, it's not particularly interesting. It has an infrared divergence integrating over t, but it's proportional to n. Here's another diagram, which I won't work out for you. It's a very similar diagram, except it has an extra watermelon in there. It turns out to be j to the fourth. There are 4 vertices now. There are 3 time integrations. I say 3 time integrations. Strictly speaking, there are 4 time integrations, but I'm only interested in relative time. So there are 3 time integrations. If you work it out, you find an extra factor of q squared and n again, same n. So this diagram scales with n, not with q, but scales with n the same way that this one does. Here's another diagram. In this diagram, 2 of the neighboring fermions interact with each other by the exchange of a kind of melon. If you work this one out, again, you'll get j to the fourth integral d cubed t. You'll get a q to the fourth, but no n. It's down, it's smaller by a factor of n than the previous diagrams. In fact, if you look at all diagrams, whoops, I'm sorry, what happened here? Just bear with me. Yeah. You'll find a whole sequence of diagrams of different powers of n in the denominator and different numerators with different powers of q. Here's another very strange diagram. In this strange diagram, the red propagators are not contained within melons. That's an interesting signal of something peculiar. It turns out that diagrams of this type here are not only down by factors of n, they're down by exponential factors of n. They're non-perturbative and they're negligible. They're infinitely small when n goes to infinity relative to any power of n. So we ignore them. Okay. What does the whole perturbation series look like? The whole perturbation series looks like a series of terms of decreasing or increasing powers of n in the denominator. Each power of n has an infinite order polynomial in it. Many, many diagrams contribute to the same power of n. And the polynomial depends on q. The polynomial is a polynomial in q. And it's an infinite sum. Plus these non-perturbative crazy diagrams that we don't care about. That's what, and this n to the a here is just a normalization of the amplitude that depends on whether it's a vacuum amplitude or a scattering amplitude, 2-particle, 3-particle, that's not important. This is the kind of answers that you get. A 1 over n expansion, to put it bluntly, a 1 over n expansion with the numerators being functions of q. I want to compare that with the 't Hooft expansion for gauge theory. The 't Hooft expansion looks identical with change of symbols. It's a sum of polynomials or functions of the 't Hooft coupling constant. Now, the reason I don't call the 't Hooft coupling constant lambda like everybody else does is because we already have at least 2 uses of the term lambda. So I've called the 't Hooft coupling constant alpha, functions of alpha divided by powers of n plus non-perturbative things. The non-perturbative things might be instantons. We don't care about them. Look at the similarity of these 2 expansions. They are very similar. And in fact, if we consider that similarity, we see something interesting about the definition of the scaling law. Q squared over n is equal to lambda. That's very similar to the large N 't Hooft scaling that alpha, which I say is like Q squared, divided by n Yang-Mills is G squared Yang-Mills. So it seems in some way that the properties of the expansions are similar, with Q squared playing the role of the 't Hooft coupling constant, lambda playing the role of the Yang-Mills coupling constant, and otherwise the expansions are very similar. Okay, does anybody want to ask any questions at this point? These identifications, I think, are extremely important to the structure of the double-scaled SYK system. I'll say it again. Lambda is like the Yang-Mills coupling constant. Q or Q squared, it doesn't matter much, is like the 't Hooft coupling constant. All right, now let's consider the different limits that we can have. Let's take first the gauge theory. I've plotted the n of the gauge theory vertically and the 't Hooft coupling constant horizontally. The ordinary 't Hooft limit corresponds to fixing alpha, fixing the 't Hooft coupling constant, and letting n get large. In other words, moving vertically upward here for different values of alpha, but always moving vertically upward. There's another interesting limit. It's usually called the flat space limit, in which the theory really has sub-ADS locality. And that's the limit in which G squared is fixed. In other words, the limit in which alpha over n Yang-Mills is fixed. And that means moving along lines of constant slope. That's the flat space limit, moving way out here. And it's different than the 't Hooft limit. They're different limits. They're related to each other, but they're quite different. The easier limit from the point of view of ordinary field theory is the 't Hooft limit, and the flat space limit of fixed G squared, that's the fixed G squared limit, in which alpha blows up. That's a more difficult limit. Now, what about the SYK system? We've said alpha is like Q squared. We've said, well, n is like n. And lambda is like G squared. So what are these limits? If you proceed vertically upward, that's fixed Q squared. That's the standard SYK system for different values of Q squared. Larger and larger Q squared as you move to the right, but it's standard SYK scaling. Double-scaled SYK is moving along these radial lines in much the same way as the flat space limit of gauge theory is moving along similar lines. We can expect the ds-SYK limit to be a difficult limit, one which is hard to think of if what we understand is standard SYK system, which is moving vertically. But that's our job now. If we want to understand ds-SYK for fixed lambda, we have to learn how to move along these lines like so, which is analogous to moving along similar lines in gauge theory. That's a lesson which is, well, interesting. Now I come to confinement. I don't know, how much time have I been going? I've lost track. Do I have lots of time or not lots of time?
You have plenty of time.
Plenty of time. Good.
Yeah.
Good. All right. It's confinement. Looking at the similarity of these two, we might ask, is there anything in the dynamics of ds-SYK which resembles the dynamics of large N gauge theories? And I say yes, there's something which closely resembles it. It's the existence of a non-perturbative scale, which I'll call the confinement scale. I'll sometimes call it the string scale.
Can I ask a question?
Of course.
This is Dongsu. Normally SYK is dual to ADS.
Yeah.
Anti-digital,
Yeah, at low temperature, I think what we know is all of these theories moving up here tend to an ADS limit.
So my question is, why suddenly, the zeta space is coming out?
It's only the zeta space at infinite temperature.
Okay.
The usual limit is 0 or almost 0 temperature. We're talking about strictly, let me get my red pen here and say ds-SYK infinite is only at infinite temperature that is expected to be true. I'll tell you what the connection is. it is through something which is not terribly familiar unless you've studied the recent papers of Witten and his friends and other people. Infinite temperature is the situation in which the entanglement spectrum of the thermal ensemble is flat. It's the limit in which the entanglement spectrum, I don't have another word for it, I'll just call it entanglement spectrum, is absolutely flat. It is connected with these von Neumann algebras that are called type 2-1 or whatever, which are believed to be fairly unique to the de Sitter space, although there may be other examples of them.
Okay.
So
Okay,
yeah, and it's a good question, and some of that question is at the root of the skepticism, I think, about this proposal. Okay, let's talk about confinement. The string confinement scale, except as it appears in DSSYK. I conflate string and confinement in the following sense. There is a confinement scale in gauge theories, and it is also the scale of the electric strings of the electric flux tubes that appear in the confined theory. In fact, there's one non-perturbative scale. It can be called string scale. It can be called confinement scale. You can call it other things. You can call it the infrared cutoff scale. The string scale, and I'm just going to call it the string scale. The string scale would be visible in QCD if you don't need to sum all the diagrams. All you need to do is to sum the planar diagrams. Planar diagrams, otherwise known as genus 0 diagrams. The planar diagrams, which are the leading n, the leading expansion in 1/n, are enough to see confinement. In the same way, I maintain that the non-perturbative string-like behavior of DSSYK can be seen in the analogous sum, the Mellon sum. The sum of Mellon diagrams is analogous to the sum of planar diagrams, and in terms of this expansion here, it simply corresponds to the first, I didn't mean to do that, the first term in the expansion here. Those are enough to see confinement in both cases. So let's talk about the DSSYK system. And let's look at this diagram again. We worked out that diagram before. It had a bunch of numbers in front of it, n dependencies, q dependencies, whatever, but it had a peculiar integral dt if we wanted to integrate over the relative position of these. It's infrared divergent, badly infrared divergent. Well, so is perturbation theory in gauge theory because of the masslessness of the gluons. This incidentally is connected with the masslessness of the fermions in the theory. The masslessness of gluons would lead to similar infrared divergences in similar vacuum diagrams in gauge theory. So there's first of all infrared divergences. Now, what cures those infrared divergences? In gauge theory, it's the non-perturbative confinement scale. Scales bigger than the confinement scale, these diagrams go to 0. Is there anything analogous in SYK or in DSSYK? And how do you see it? Well, you can see it from sums of Mellon diagrams. These are all leading n diagrams in which there are melons, inside melons, inside melons, and inside melons, and so forth on each rung here. They can be summed up. They're summed up by Schwinger-Dyson equations. I've never quite figured out who was the first one who, I keep asking people, were you the first one to do this? And they say, so no, somebody else was the first one to do it. And it's gone around in several closed loops by now. I don't know who was the first one to do it. But I know that it appears in papers by Maldacena Stanford and by Roberts, Stanford, and Stryker. And I suspect something like it appears in paper by Chi and Stryker. But whoever first put it together, here's what happens. This diagram, as a function of the time between the two endpoints here, instead of just being independent of that time, turns out to be 1 over cosh squared qjt, t being the time between here and here. This integral now over the relative times becomes convergent. There is a clear sense in which there's an infrared cutoff scale which emerges, and that infrared cutoff scale is just 1 over qj. Just look at the form of the integral here. It is cut off at a scale in which the time is equal to 1 over qj. And furthermore, the integral itself is just given by something proportional to 1 over qj. That suggests that there is an infrared dynamical phenomenon happening which cuts off the infrared scale and which is analogous to the confinement scale or string scale of QCD. Where does it occur? It occurs at an energy scale, ms, which is just q times j. Remember, j is the smallest scale, the smallest energy scale in theory. N times j is the biggest scale, and here's q times j, which appears as a string scale. Now let's go back a second. If you remember, you may not remember, but I'll remind you.
I have one. In
Say
this
again?
calculation, is it Euclidean is important or it
No.
could be-
I'm definitely not thinking Euclidean. You could. No. This is
Lorentz, yeah.
yeah. No. This is. It wouldn't matter, but I think it's. I find it easier to think about this in Minkowski signature. In any case, however you think about it, if you remember this middle scale, this median scale, the scale that lied halfway between the maximum and minimum, that was j times the square root of n. The string scale is q times j. And if I look at the ratio of them, the j's cancel out, and I get q squared over n. These were the two definitions of lambda, which I told you eventually would turn out to be the same definition. So, in fact, yes, there is a non-perturbative scale. It is analogous to the confinement or infrared cutoff scale of gauge theory. And it tells us that this quantity lambda is both, has a significance in both sides of the duality, in the gravity side of the duality and in the SYK. Now let's come to confinement. There are too many degrees of freedom chi if they were all to be allowed to be emitted into the static patch in the form of Gibbons Hawking radiation. I mentioned that before. There are n of them. Gibbons Hawking radiation usually is very sparse. Do you know how many? Anybody want to make a guess? I'm going to entertain a guess from you. How many? If there was just photons, if the only light fields were photons and gravitons, how many quanta, Hawking quanta, would we expect to exist in all of the observable part of de Sitter space? The observable part, I mean, out to distances 2/3 or 3/4 or 9/10 of the cosmic radius. Well, I won't really ask you, I will tell you. Exactly one photon or one graviton in that entire observable universe. And it's a graviton of wavelength equal to the radius of the universe. Not very much energy stored in it, extremely sparse. But if all of the large N fermions were to be emitted and not be confined to the region near the horizon, you would have a mess of a large number of particles, Hawking quanta, in the observable part of the de Sitter space. That's not what happens. That's not what should happen. The conclusion must be, we could just decrease the number of fermions. Why don't we just cut down the number of fermions? Well, we need those fermions to provide the entropy of the de Sitter space. We need all of them. So they've got to exist. On the other hand, they cannot propagate deep into the bulk easily. And so they must, in some sense, be confined to the region near the horizon. In fact, I think I'm going to accelerate a little bit here. I'm going to jump a step. Well, no, let me tell you why. In fact, in 2+1 dimensions, there are no gravitons. So Hawking radiation in 2+1 dimensions can't be gravitons. It could be photons if the theory has photons. But in order for SYK as a bulk theory to have photons, you have to consider the complex SYK system, the system in which the fermions are not Majorana fermions, but are complex fermions. In other words, the fermions allow a definition of a U1 symmetry. That U1 symmetry becomes the electromagnetic U1 symmetry. That's easy to do. You don't lose very much. You just go to complex SYK system with a U1 symmetry. And all of a sudden, you have photons. That's good. If we have photons, we have a chance of having some Hawking radiation. There's another symmetry. The other symmetry is not a real symmetry, and I'll explain what I mean by that. It's a symmetry of the ensemble average. We're averaging over this ensemble of J couplings. That's what SYK system does. But it's not a symmetry of any one of the instances of a choice of J's. It's only a symmetry of the random average over the ensemble of coupling constants. And that symmetry is SUN, where it acts among the fermionic degrees of freedom to transform them one into another. As I said, it's not a symmetry of any one of the instances of a choice of coupling constants. It is only a symmetry of the ensemble or statistical average over them. That's a peculiar thing. We don't usually think about things like that in the ordinary world. And what I'm going to tell you is the confinement that I'm talking about is confinement of the charges in this ensemble SUN. That is a radically new thing that I have not seen before, where a statistical average with a certain symmetry gives rise to dynamics, which in this case is confinement. And I will do it by doing a calculation. Let's consider a chi-chi bar pair, a pair of charged fermions, anti-charged fermions, not a pair of one fermion, one anti-fermion. The fermion-anti-fermion system could exist in a singlet state. The singlet state is the sum over I of chi bar chi. That's the equal superposition of any pair, chi bar 1, chi 1, chi bar 2, chi 2, and so forth. That's the SUN singlet configuration of a pair. And then there's the adjoint of SUN, which corresponds to, again, chi bar chi summed over I and j with any tensor whose trace is 0. There are a large number of adjoint states, n squared minus 1, and there's only one singlet. So the singlet is very sparse, only one of them, many, many adjoints. Okay, so you might think any statistical average would the adjoint would dominate because there are just so many of them. Okay, so let's see what happens. Let's imagine a scattering diagram between an I bar and a J bar. I and J now label which of the species, which of the flavor of fermions we're talking about. The leading scattering diagram is this melon. It's not a complete melon. It's missing 2 pieces here and 2 pieces here. The melon connecting them. That's the leading contribution to it in SYK, and you can work it out. This factor is the numerical. Well, it doesn't matter much. This factor Q minus 2 is there because you've peeled off 2 fermions from each side over here. There's a J squared corresponding to these 2 vertices. There's the red dotted line, which is this J squared over Q factorial over Q to the n minus 1. And finally, there's an integration over the relative times of these 2 vertices, and that gives you this factor 1 over Qj that I described before. All of this gives you Qj over n. and it's small because it's 1 over n. On the other hand, there's also a matrix. The matrix is a matrix in the space of 1, 1 bar, 2, 2 bar, 3, 3 bar. And if you work it out and look at the structure of the diagrams, you find that any II bar can go to any JJ bar. Any II bar can go to any JJ bar. So the matrix structure of this diagram is ones everywhere. Any II bar can go to any AJJ bar with equal amplitude. Now I'm going to interpret this as a potential between I and I, or between the two fermions, as a potential energy between them. I won't try to justify that here and now, but it's not surprising that you draw a diagram with an exchange and you relate it to a potential energy. That's kind of familiar. What is the potential energy between the I and the I bar? Well, this matrix has n eigenvalues. It has one eigenvalue, which is equal to capital N, and n minus 1 eigenvalues, which are equal to 0. And that's because this matrix is a projection operator. It's a projection operator onto the singlet state. The singlet state is 1, 1 bar plus 2, 2 bar plus 3, 3 bar, etc. So this matrix is a singlet projection operator. No, it's not quite. It's n times a singlet projection operator. Why n? Because its trace is n, and a projection operator onto a pure state has trace 1. So this matrix here, which appears here in this potential, it's a matrix potential, is n times the projection onto a singlet, and this is what this tells us. It tells us, well, the eigenvalue for the singlet is n, and the eigenvalue for the adjoint is 0. So it tells us that the potential for the singlet state of fermions is deeply negative, minus Qj, and the potential in the adjoint combination of fermions is just 0. The energy diagram looks like this. The singlet is way down here at deeply negative energy, and the adjoint is up at 0 energy with a big gap between them. Now, something's wrong with this. We don't expect a deeply negative energy for these things. That would mean the theory was unstable somehow. And in fact, I will tell you what's wrong with it. We've left out something. We've left out the possibility that the fermions themselves, where are they? That the fermions themselves have energy, a kind of mass. This is the potential between the two fermions. There's also the energy of a pair of fermions. You might say that's 0 because these fermions are nominally massless, but I don't think that's true. I think they're no more massless than quarks are massless. Quarks have a mass in the Lagrangian, which is massless, but if you try to isolate a quark, guess what its energy is? It's infinite because it is attached to an infinite string. I think these fermions have large mass in the same way, and we can even try to calculate it. Where does that fermionic energy come from? Here's a single fermion. Here's the horizon. The horizon has a large number of fermions in it, and we can calculate a diagram which represents the potential energy between a single fermion and the horizon itself. The horizon you can think of as a condensate of a large number of particles. You can work it out, and you get something which is again proportional to Q times J. I'll just call it epsilon chi. The bottom line, if you put everything together that you know, is that there is an additive contribution to the energy of the singlet, which is down here, was down here, and the adjoint, which is up here, which shifts them both up by an amount equal to the energy of the two fermions themselves, and appears to require that the singlet gets shifted up to 0, and the adjoint gets shifted up to a large mass, which is Q times J. Now that's very interesting. Oh, it also shifts the mass of the single fermion from 0 to Q times J. And what that is suggesting is that the singlet winds up having no energy, and all of the objects which transform non-trivially under the SUN have a large energy. Confinement of charge, confinement of the gauge generators or the generators of the SUN. That seems to be what's going on. There are many examples of this. There's no complete universal proof of it yet. There will be. That all energies get shifted up, I suspect, by the Casimir operator of the relevant representation. And that means that the only remaining states of the system which are light enough to be emitted as Hawking radiation would be the singlets under this SUN. There are very few singlets, as a matter of fact, and the number of singlets does not increase as the N of the gauge theory increases. The number of singlets is just the number of ordinary hadrons for QCD, and that does not increase with N. All right, so let me give you now an analogy for what's going on. The analogy comes from, yeah.
As far as you understand, you are considering infinity structure.
Say it again. Go slow.
Yeah. So as far as I understand, you are considering infinite temperature given in the propagator. So
this is not the Hawking temperature. This is a formal mathematical temperature, which is equivalent to saying the entanglement spectrum is flat. The Hawking temperature is a derived emergent quantity. It appears in a paper by Lin and myself where it was called temperature, but it is not the temperature that you would identify with the Hawking temperature.
So the Hawking temperature is actual temperature of the system. So
well, it's the actual temperature that you would feel if you sent the thermometer out into space and then pulled it back in and see what it recorded. It is not the mathematical temperature which determines the thermal field double state of the collection of fundamental degrees of freedom. And that is connected with the flatness of this entanglement spectrum. So I didn't really want to get into it. You had Witten give you a lecture on it. He may not have called it infinite temperature, but the only ensembles which have flat entanglement spectrum also have infinite temperature. But it's a mathematical temperature. It's the Boltzmann weight in the mathematical SYK system, and one has to calculate what a thermometer would read. That is the content of the paper that I wrote with Henry Lin, defining a quantity called temperature, which I think is a little too much for one lecture today to get into that. I'm going to beg off it and say, read the paper by Lin and myself.
So one more. In equilibrium, is it possible? I mean, bath temperature and system temperature can be different?
Yeah. And yes. Yeah. You're thinking a good thought. You're saying, why isn't the horizon degrees of freedom in thermal equilibrium with the bulk degrees of freedom? I think that's what you're asking.
Yes.
Why don't they have the same temperature?
Yeah.
The answer is that there is no such thing as the horizon degrees of freedom and the bulk degrees of freedom. There is only the horizon degrees of freedom, with the bulk degrees of freedom being emergent combinations of the horizon degrees of freedom. So this is not a question of the thermal equilibrium between two sets of degrees of freedom. It's the issue of finding how the bulk degrees of freedom emerge out of the boundary degree, out of the horizon degrees of freedom. I'm going to leave it there because I can't do it justice now in the next 5 minutes.
Okay. Yeah,
so it's discussed in the paper by Lin and myself. The paper is called "Infinite Temperature is Not So Hot," and you can imagine why. Okay, but the analogy, not for that, but for other things, comes from QCD, the large in QCD. Imagine a bubble of plasma, QCD plasma. That's the pink thing here, a plasma bubble. Does a plasma bubble evaporate? And if so, how fast? You might think that a plasma bubble can evaporate into gluons. And there's a huge number of species of gluons. And so you might come to the conclusion that the evaporation is very rapid. The luminosity being proportional to the number of species of particles which can carry off the energy. And you would say the luminosity is like N-Yang squared. That's the number of gluon species. What would that mean? That would mean an incredibly rapid decay, and the plasma ball would disappear in no time at all. Plasma balls don't work that way. QCD plasma balls don't work that way. They have a lifetime and a luminosity and all those things. The lifetime is long, the luminosity is small, and by small, I mean it does not depend on N. So what really does happen? What really does happen is the non-singlets of the gauge group now, of the, let's say the gauge group is SUN, like it would be in QCD, large N QCD. The non-singlets are attached to the plasma ball by strings, by electric flux tubes, if you like. If you try to extract a quark out of the plasma, it will be connected to all the QCD charge that's present in the plasma ball here, and it will be connected by a string. Therefore, it will be very costly in energy to pull this quark out, and the plasma ball will not evaporate to quarks. Likewise, over here, I have a gluon. This is the red-green gluon, so to speak, or the red anti-green gluon. It's not two particles, it's one particle. And it is connected to the plasma ball by a pair of strings. So neither neither gluons nor quarks, although there's a huge number of species of them in the large N limit, can be emitted, and the plasma ball does not decay that way. Can the plasma ball decay? Yes, it can decay by emitting singlets. What is a singlet? A singlet is a QQ bar pair, but it's got to be a QQ bar pair in the singlet state, in the non-colored state. It can emit glue balls. Glue balls are also singlets, but the number of species of glue balls does not grow within, and the number of species of mesons does not grow within. So there is no danger, in fact, of the glue ball evaporating too fast. It's just almost everything is confined to the surface or cannot get out beyond the surface of the glue ball. That's the analog. There are very few singlets. The evaporation is slow and independent of N. The only difference is in the SYK system, the gauge theory, it's not really a gauge theory. The thing which defines what a singlet means is this fake ensemble symmetry. Those are the charges that appear to be confined. And I'm not postulating that. I'm doing it by calculating the potential between pairs of quarks, not pairs of quarks, pairs of fermions. Okay, let's make one more comment that in 4 dimensions, as opposed to this 3-dimensional or 2-dimensional SYK system, it's expected that the holographic degrees of freedom of de Sitter space are matrices. Matrices themselves. That appears in the works of Banks, Fiol, and Morrissey. It appears in a paper of my own, which said that there's good reason to think that in 4 dimensions, the holographic degrees of freedom are matrix degrees of freedom. And therefore, the theory would have a true SUN symmetry. True in the sense that that there would be a genuine SUN symmetry of the system and not an ensemble average SUN symmetry. My guess is that in higher dimensions, or in particular in 4 dimensions, that the horizon degrees of freedom continue to be confined to the horizon, but confined in a more traditional sense by a gauge symmetry, which the theory actually possesses. Other than that, I would say my guess is that these principles or these phenomena which I've described are general for the Sitter space, even if this DSSYK system proves to be not quite the Sitter space. Okay, I'm largely finished. If you want me, I can summarize what we said. Yeah, let me just summarize. The first thing is in the semi-classical limit, where the horizon gets very, very big, there's a separation of scales. There's this very large, now I'm talking about the three-dimensional system. There's this Planck scale, which is the biggest energy that you could put in. It becomes infinite in the large n limit. There is the Hawking temperature or minimal scale, which goes to 0 in the semi-classical limit. And there's the scales in between, which define all the normal things that we're used to talking about in our ordinary world. And they sit somewhere in between. In 4 dimensions, this would be the Planck scale. In 3 dimensions, it's this M scale. And there are other scales, particle physics scales, string scales, and so forth, which are presumably not very far, by comparison with these distances here, not very far from this microscopic scale here. That's this idea that there's a ratio of ms to m, which is finite. And if you do remember, yeah, here it is right here, the ratio of ms to m, which I called lambda, turned out to be q squared over n. So if you want to keep the ratio of these scales fixed as you go to the semi-classical limit, you are forced to a limit in which q squared over n goes to a limit. And from one point of view, that's why the double-scaled limit is the relevant limit for a de Sitter space with a fixed ratio of string to microscopic length scales. We talked about the confinement of SUN charges. Almost all the degrees of freedom are confined to a vicinity near the stretched horizon. Only a terribly small fraction of the degrees of freedom get emitted as Hawking radiation into the bulk, into the, and it's very easy to miss that very small fraction if you do a statistical average over everything. So it's a subtle business picking out what can actually be emitted. In the case I described, it's the singlets, but the singlets are a very, very small fraction of the possible things that you can make out of a system of fermions. I haven't talked about sub-ds locality, and I think I won't here. I think I'll just leave it at that. But I will tell you that there is some tension. I don't fully understand the tension. My friends who are experts at this DSSYK system tell me that a different analysis, an analysis based on chord diagrams, seems to be in tension, in particular in tension with some of the scalings, which I reported and explained. I'm guessing that they're wrong, that if they do everything correctly, and in particular account for the fact, for this confinement mechanism, they will find that the chord analysis is in agreement with me. But I don't know. At the present time, it's in the air. Will it turn out that this DSSYK sub infinity is a model of de Sitter space, or is it something else? I would say I don't know, except I think I know. My friends who are very expert at this are not willing to say that it's wrong. They're willing to say that there's some tension. And that's where the situation lies now. I would say this is a big deal. If for the first time we have a genuine holographic model, a tractable holographic model, which represents de Sitter space, I personally think that's a very, very big deal. We do live in de Sitter space. We don't live in anti-de Sitter space. And I'm hopeful that this DSSYK system will prove to be the first genuine concrete holographic model of the sitter space. I will leave it at that. I've used up more than enough time. I've gone almost an hour and a half now, I think. So that's what I came to tell you. And I hope you have learned something from it. I realize I probably told you too many things. That tends to be in the nature of theoretical physics seminars. But anybody, if you want to, here's a question. Do you want the notes from the lecture? In other words, these notes here? I can send them to you.
Yes, please. Yeah, it will be very helpful.
All right. Who do I send them to? Just the usual contact that I have?
Yes, yeah,
Yes.
please, yeah, send me. Yeah.
Okay, who are you again?
This talk, yeah, or
Yeah.
You can send me separately, and this video and your lecture.
I'll
will be
just send it.
uploaded.
I'll just send it to my contact.
Yes, please.
Okay, I can do that. And good. If there are any more questions, I'll be glad to handle the questions now. But
I have a question. Am I audible?
Go ahead.
Hi. So when you
Hi.
talked about this confinement mechanism in the potential, we had to really go and resum out all the melodic diagrams, right?
Yes. Okay. So let me go back to it. Just I know what you're saying, but let me just all right. Here we are. No, not that one.
Yeah, the other one. But my question is really relating this. So this is how we saw confinement in the potential by resumming melodic diagrams.
Right. So implicitly, there's lots of little things in here.
Right. Exactly. But then when you talked about this mass for the adjoints, like when you had to shift it, we talked about we really thought about a potential between the horizon and the far away excitations, right?
Well, what does far away mean now here? We're dealing with a system which is really 0 + 1 dimensional. And the notion of far away is an emergent notion that doesn't appear at the level of this kind of thinking. But yes.
Right. But the second diagram you showed, I'm trying to understand what is that calculation exactly.
Okay, so all right. This is a guess about how it works.
Yeah. Sorry.
However, that something like this has to be true follows from other facts, which I eventually gave up trying to explain because it was getting too late. But let me tell you what it is. Here was the status before we worried about the single particle excitation energy. This was negative, and the adjoint was 0 energy. Remember?
Yeah.
Okay. So this is inconsistent. This cannot be the case. Or for the energies itself. It could be for the potential energy, but it can't be for the total energy for the following reason. Something's wrong here. Let's imagine calculating. Let's take this singlet operator and imagine calculating correlations of it. Okay, now the singlet operator happens to have another meaning. This sum, chi bar I, chi I, you know what it is? It's actually the total charge, U1 charge. Does that seem familiar? Hello?
Yeah, go ahead.
All right. Because it's the conserved U1 charge, that means correlation functions of it have to be time independent, exactly time independent. On the other hand, if the singlet were to have had an energy E, you would expect oscillations of the form e to the minus or e to the IET in correlation functions. Correlation functions of operators which introduce an energy E into the system will oscillate. On the other hand, on very general grounds, the correlation functions of these things cannot oscillate. And therefore, the energy cannot be just the potential energy. What else is there? The single particle energies. We don't know what the single particle energies are. This was just a kind of an intuitive model to try to guess how it might work. But the single particle energies have to be enough to, let's see, where's my picture, to raise this up to 0 because otherwise we would have a conflict with the conservation of chi bar chi. So I would say we know on general grounds that the final output energy for the singlet has to be 0. And the only way that I can understand how that happens is if the whole spectrum gets lifted up. But I think there's a lot of work to be done to find out if these ideas make good sense or not. I'm not going to tell you that I'm 100% confident in what's going on here. I'm not. So there's much to do. This is my overall picture of how I think the thing ought to work. It's closely connected. If you're familiar with how hadrons work and so forth in QCD, you will recognize some of these things. You will even recognize this uplifting phenomenon. It's closely connected to something that does happen in QCD, but I don't have time for it now. So we'll leave it at the level of saying these are conjectures. They're certainly conjectures.
Yeah, thank you.
I'm not sure if that answered your question or not.
Yeah, I was wondering if I just go ahead and include the melonic resum all the melonic diagrams, would I get this lift or not in the potential calculation? Because that was one way you said confinement, and this mass generation.
Okay, so my guess, I think not. Okay, I think it's very much like QCD, where if you try to calculate the quark mass at every order, you would find the quark mass is exactly 0. That follows, in fact, from helicity conservation of in diagrams here. Let's just draw it. Here's a quark. Here's a gluon. The gluon diagram cannot give a mass to the quark because it would require a mass requires a helicity flip, and the gluons conserve helicity. It doesn't matter how many of them there are. Doesn't matter how many loops there are in these. Just in a trivial way, the QCD sum of diagrams, or the QCD individual diagrams, can never give a mass. And if you didn't know about the confinement phenomenon, you would say the mass of a quark is 0 equals 0 equals 0. On the other hand, the confinement argument tells us that a quark is a thing which must be connected to a string. That string has to have an end someplace, or else it must go off to infinity. If it goes off to infinity, the mass of the quark is infinite. So a free isolated quark has an infinite energy that you can never see by summing diagrams. So my guess is that it's a hard job to see. Well, okay, let's leave it at that. At the moment, I think that determining the energy of a free fermion away from the horizon is analogous to understanding the mass of a quark far away from any other, from the plasma condensate, if you like. Again, I emphasize that I am less confident of these ideas than I think I have ever been about anything, any conjectures that I put forward, but we're going to find out.
Related question. Is there any evidence, numerical evidence based on your double scaling limit? I think it may not be much difficult.
Well, I have no idea how you would do numerics for this double scaled limit. First of all, you've got to get to large n to distinguish n from square root of n. If we only had 10 qubits, square root of 10 is 3. It's hard to tell that there's a gap between 10 and 3. So you got to get a pretty large number of qubits. But second of all, you have to have a Hamiltonian, each term of which involves the square root of n degrees of freedom. I don't know how you would engineer that. Well, you're talking about numerical simulation by classical computation? That's
Yes.
way out. Yeah, there's no way to get enough fermions into a classical computation, I think, to test this. It'd be very, very hard. And I'm not sure what you would test. I think it's very much like trying to test QCD. Well, I haven't given it a lot of thought. Maybe, we do test QCD by numerical computation, don't we? Monte Carlo and so forth. Who knows? I take it back. I don't know if there's a way to test it. Maybe there is. It would require setting up the system for a computer, and then going and doing Monte Carlo analysis of it. And yes, maybe there is a way. What would you want to test? This confinement idea?
Yeah.
Maybe it is possible. Maybe it is possible. By something along the lines or analogous to lattice gauge theory, maybe. And Monte Carlo, yes, maybe it's possible. The whole point of SYK, though, is it allows you to get around that and not do it by doing ensemble averages. Ensemble averages are the trick which allow you to answer questions without doing numerics. So I would think the more likely way to establish these as facts would be analytic, using appropriate ensemble average tricks. But again, that remains to be seen.
Is there other question?
Leonid, so do I understand correctly that this confinement is something you expect in this double scaling limit that give you the zeta rather than only in that limit? So conventional ADS limit.
Yeah, I think I have used infinite temperature in here in the structure of the Feynman diagrams.
Mm-hmm.
I have used infinite temperature. Yes, I did use the double scaling limit. Yeah. I did not use the assumption that DSSYK infinity is de Sitter space. These diagrams here do not depend. They're just the diagrams from DSSYK infinity. Mm-hmm. Yeah, this one, for example. I didn't use the assumption that it's dual to de Sitter space. I just calculated it.
Right.
And I found out that the singlet and the triplet, the singlet and the adjoint are separated by this large energy. So in that sense, I did not use the de Sitter connection. I did use the double scale limit.
Right, I understand. Okay. Thank you.
But on the other hand, the connection is that de Sitter space, in order for it to define a reasonable bulk without a incredibly large number of quanta circulating around in it, requires somehow the degrees of freedom to be confined to the horizon. You need a lot of a degree. Here's the tension. You need a lot of fundamental degrees of freedom to account for the large entropy, and most of them must not be able to leak into the bulk. That's the tension. That you need a very large number of them, whether it be DSSYK or anything else. You have a huge number of degrees of freedom in order to account for all the entropy, and most of them must be confined to the horizon. Otherwise, you would have a bulk which was just filled with an unreasonable number of quanta.
If there is this digital limit, as you were telling us about, and there was this more conventional ADS, well, exactly what would be in between? What would be sort of scaling that give us?
Oh, that's a very interesting question, and that's the source. Yeah, the answer is I don't know. That is the source of most of the controversy or the tension that's arisen about this. Is how do you extrapolate? How do you extrapolate between the two things where you think, I think I know what I'm doing at one end. Everybody else, including myself, thinks we know what we're doing at the other end. How do you extrapolate between them? And that's exactly where the tension comes from. So the answer is I don't know. And I can tell
Any
you,
other-
I haven't named the people who, there's nobody who says I'm wrong. There's people who say there's attention. We have, in order to make sense out of what you're saying, we're going to have to fill in the gaps between of the kind you just said, and we don't see how the connection works. Okay, these are people who are great experts at this subject. They're people who have contributed an enormous amount to the subject, and I take them extremely seriously. So, although I don't understand their arguments, I'm quite worried about them.
Thank
You can
you.
try to guess who they are. You'd probably guess correctly. They only they don't include Maldacena. That's the only thing I'll tell you. Well, they're all people at Stanford. All people at Stanford under the age of 40. Under the age of 40. You wouldn't have a hard time figuring out who they are.
Mm.
Right. So
any other question?
So I have a question. You talk about the scales in 4D and 3D. Is there any analogous explanation 2D? I mean,
Oh, in 2D?
Yeah. For
You know,
this,
I have
like JT, is there any connection between JT scales and
well, no, what I'm
scale
telling you
scales?
is that JT in many respects works more like a three-dimensional theory than a two-dimensional theory. By a two-dimensional theory, it works more like, because of the dilaton. The dilaton is effectively the radius of a third dimension. And it works more like a three-dimensional theory, which has been dimensionally reduced, than it does a two-dimensional theory itself. Let's see. Yeah, the starting point is really a 2+1 dimensional theory, which when dimensionally reduced in a certain way, gives rise to the JT system, which is two-dimensional plus a dilaton. The dilaton here is a signal that in many ways the theory is closer to 3 dimensions than 2 dimensions. So everything I told you about scales, good. So everything I told you about scales here in 3 dimensions is also true for the JT 2-dimensional system. Where is it? Yeah. Everything I told you here would apply almost exactly in the same way to the 2-dimensional system.
Oh,
It wouldn't apply to pure 2-dimensional gravity. It applies to 2-dimensional gravity with a dilaton, with the details being such that the cosmological constant of the JT gravity is positive rather than negative. So I just use the 3-dimensional as a trick to understand the JT system. So all of this would be the same in JT in the 2-dimensional version. Does that answer the question?
So we can write these in terms of the parameters of JT, like S0 or with end of the word brain, like the number of colors.
I don't know about end of the world brains, but yes, you can write all of these things in terms of the JT system.
Thank you.
With the dilaton just replacing the radius of the additional dimension.
I see. Okay. Thank you.
Yeah. Yeah. So I should have said that. I mean, that's an important point that the JT system has exactly the same behavior as this. And the three-dimensional theory is just a trick to well, I'm not sure which is a trick. Is the theory really 3-dimensional and dimensionally reduced to make it easier, or are we interested in the 2-dimensional theory and just using the 3 dimensions as a trick? I don't know. Not important, I think.
Any other question? If not, let's thank speaker again.
Okay, thank you.